Hello friends, today we'll be discussing about a central theorem in matching theory, which is the existence existence theorem for the existence of a perfect matching. So let me state the theorem formally. So suppose G is a bipartite graph with vertex set E and edge set E, bipartite. Then there exist. So suppose I'll say if for every subset S of V, the following holds: the cardinality of S is less than the cardinality of n of S. So also let me just bifurcate V into V1 union V2, where V1 and V2 are independent set. Because it's a bipartite graph, you can always find two partites V1 and V2 such that V1, both of them are independent set. So suppose this condition holds, that if S is a subset of V1, uh, then the cardinality of S is less than equal to cardinality of neighborhood of S. Neighborhood of S is basically all those elements that are connected through an edge to elements of S. So if this condition holds for all, if for all S this holds, then there exists a perfect matching. Then there exists a perfect matching. So let's try to get a motivation on why this actually holds. So consider the following bipartite graph, some arbitrary bipartite graph, something like this. So you'll notice that if you, so let's call this V1 and this call this V2. So obviously for a matching to occur, you will obviously have this condition that V1 should always be less than equal to neighborhood of V1, which in this case is V2, right? Or else there will not be a matching. There will be less number of elements there, so there will not be a perfect matching. Now suppose if you have such a perfect mapping, and suppose you ignore this some specific matches out of this matching, the resultant would still be a perfect matching. You can see that now. So what does this say is that for a subset, so for any subset also, the neighborhood, this condition should hold. This is not entirely accurate, but for the sake of intuition, you could see that why this holds. So all these conditions seems like a necessary condition, right? Necessary condition. What the theorem adds here is that this condition is in fact sufficient condition as well. Sufficient condition. So why is that so? So we'll see that in the proof. Just to complete the statement, I should also write and vice versa. This is not really a very formal way of writing the theorems, but it's fine. Coming back to the proof, let's see why it works. So we'll do it. Yeah, so the basic idea would be to do it as an induction on size of V1. We'll do an induction on size of V1. So if V1 is 1, it's obvious, right? V1 is 1, V2 has to be 1, and then there is just simply a matching. Assuming the graph has two vertices. If it has one vertices, then the theorem is redundant, means it's vectorsly true. So now suppose this, we put an induction, suppose it is true for all V1 with size k, true. So now we will proceed for the case when V1 is k plus 1. Recall that, just write it again, V1 is V1 union V2. These two are independent set. Okay, this is still not a formal proof, because what I'm trying to do is I just want to capture the important mathematical steps involved in the proof. Alright, so we divide the proof into two cases. Also recall the central condition of the theorem is that S is less than equal to neighborhood of S for all S subset of V1. Okay. So we consider a very specific instance of this condition, that is S plus 1 is less than equals to n of S. So what basically this is saying, that since this is less than equal to, there is a possibility that this can be equal to this. So we are getting rid of that possibility. We are saying that there is a strict gap. So because they are integer values, so we just add 1 plus 1 and say it's plus 1 less than equal to n of S. Suppose this holds for all S subset of V1, then we show our theorem. So how do we do this is, given V1 and V2, suppose like this and like this, consider one any such edge and make a pair with it. and pair it with another element with v2, call it a and b, and yeah, and just mark it like this. And then now consider new kind of bipartite graph, where partite 1 is v1 minus 1 and partite 2 is v2 minus b. So just so note that just because this condition holds for v1 comma v2, it may not hold for v1 dash comma v2 dash. Yeah, this is v1 dash and this is v2 dash. It's not immediately obvious it should that condition should hold for it. If we show that this holds for v1 dash and v2 dash, then we have a perfect matching at this level, and then you could add also at this matching to get an overall perfect matching. So all our job has been reduced to showing that the subset condition, this kind of condition also holds for v1 dash v2 dash system. So how to show that? So consider any subset s dash subset of v1 dash. Now in the, I'll just write it here, in the v1 comma v2 system, we know that s dash is less than equals to n of s dash. That is because from this theorem. Now but you are in v1 dash v2 dash system. So again, so what will be the theorem? S dash, and what will be the neighborhood of s of s dash? So in the original system, the neighborhood was n of s dash. But how is this system v2 dash different from v2? It's different by the elimination of the b element. So if the neighborhood contains the b element, then if the neighborhood contains the b element, then the new neighborhood n dash of s dash is actually one less than the old neighborhood. And this is actually the worst case situation, because if it does not contain, then the new neighborhood would actually be n of s dash, and then we would have inequality state directly from the v1 v2 consideration. But so we are only considering the worst case situation, that, and the worst case situation is that s dash, the neighborhood of s dash, this is actually questionable, we don't know. Is what we know is that neighborhood of s dash is equal to this part. All right. And actually I should not write this. It's like I said, we are working in a special case, so I should also add a 1 here. So we know this holds. So if we substitute these two together, so we'll have 1 plus s dash is less than, and if I substitute n of s dash as n of s dash plus 1. Yes, we are substituting n of s dash as this one goes here, so it will get plus 1, and so 1 and 1 gets cancelled, and you have s dash is less than equal to n of s dash. Now this condition holds, which is very similar to this condition, and you are working on a smaller graph because we have eliminated elements a and b. So by induction, there exists a perfect matching here, and there already was a matching here, so we get an overall perfect matching. Overall perfect matching. Alright, just to recall, perfect matching is the matching such that every element of v1, that is the left hand side of the left partite, gets mapped to some elements on the right hand side. Alright, so this was the case 1. Now case 2 is the complement of case 1. So that would be that there exists an S naught such that S naught is equals to neighborhood of S naught. Because the complement is that it's equal to, because we have a strict condition that this side should be always be less than equal to this side, and then we divide it into two cases where it is strictly less than, and where it is actually equal to. So we'll do the same drill here as well. So we know we have v1 minus s naught. S naught is not an element, it's a set. I just written it like this. We'll call it as v1 dash. Similarly, v2 dash would be v2 minus n of s0. And then so because of this condition, we can clearly see that there exists a perfect matching here, because they are equal to, so there is one to one matching. And then there's also a theorem that by actually this is true by induction or smaller set, perfect matching by induction result. And so if we manage to show that such a situation, such a condition also holds here, that for every subset s dash of v1 dash n dash of s dash is greater than equal to s dash, then there will also be a perfect matching here, and we can then just combine these two perfect matching to get an overall perfect matching. So let's check if this is indeed the case. So consider s dash. So now we know that in the v1 v2 system, again we know that s dash is less than equal to n of s dash. Alright, but you want to check it in the v1 v dash system, v2 v2 dash system. So here we'll just look at the worst case. So if it is less than equal to, again and if it is less than equal to this, then we are done, right? So if this is the case, then we are done actually. So we have to be the devil's advocate and look at this case that s dash is actually greater than equal to n dash of s dash. Now you may ask, how is this the case? Why is s dash getting bigger when we consider n dash? Because we know that when you consider in the v1 v2 system it is less than. So the only way it is possible is that sum of the neighborhood, like n of s dash intersection n of s naught, is not empty. Some of the neighborhoods getting absorbed in the neighborhood of s naught. That is one possibility. I'm not saying this is going to happen. This is let's just me mark this, and this is not relevant for our uh, proof. So this is the only way it could happen. What will show that this will not happen at all. So assume that this is the only way it could happen, because this is the only way it could happen. So what happens is now, now consider a combined set S naught union S dash. Now here you can clearly see that their neighborhood will be n of S naught union uh, uh, n dash of S dash in V1 V2 system. So there is n dash here, it's V1 V2 system. It will be this. And what should be the sign of what is the sign of the inequality? So you know that s naught and this are equal, and you know that this is less than equal to this is bigger than this will be greater than equal to this. But in the v1 v2 system, this is a contradiction to what our assumption that n of s is greater than equal to s. This is a contradiction to that. Therefore such a situation will not occur, and hence what we get is that v1 dash system and v2 dash system has a perfect matching, and combined with this perfect matching, and this is also true because of induction, has perfect matching because it has this property, it has this property, and then it has also has smaller size, so it will have a perfect matching. Combined with this perfect matching, what we get is an overall perfect matching. With this, we have proven a theorem. Thank you for watching. We'll see you soon.